Hi everyone! Today I'm going to be going over example 1-2 in Fogler's Elements of Chemical Reaction Engineering 5th edition. In this example, we have a liquid phase isomerization reaction, which we can represent as the chemical species A reacting to become chemical species B. From the problem, we can see that this is a first-order reaction in A, which means that the rate law can be written as negative RA is equal to rate constant K times concentration of A. We're also told that the reactor maintains a constant volumetric flow rate throughout, which means nu is equal to nu naught. In some of our past classes, we may have seen nu to be written to represent velocity, but note that in this case, nu represents volumetric flow rate with the units of decimeters cubed per minute. Okay, let's now create a visual for our tubular reactor. So at the inlet, we have a volumetric flow rate of V naught or nu naught, and then exiting nu. Inlet is V equals to 0, outlet V equals V1, Ca naught, and then Ca, concentration at the outlet. Now that we have created our visual, let's answer part 1. Part 1 asks us to sketch the concentration profile. So in the x-axis, we're going to put volume. Because we know for a tubular flow reactor, we can assume that the concentration of each species remain constant radially, but varies down the length of the reactor. We know that at the inlet of the reactor, or at V equals 0, concentration of A is equal to Ca naught. And as we proceed down the volume of the reactor, A gets consumed. So Ca at V1, which is what we see up here in our diagram. Okay, now let us move on to question 2. So for this question, we are asked to derive an equation relating the reactor volume V to concentrations, rate constant, and the volumetric flow rate, or in other words, write V as a function of Ca, Ca naught, the rate constant K, and volumetric flow rate. And since in our case, volumetric flow rate is just constant, we're just going to put that as nu naught. So recall the mass balance equation that we derived for PFRs in chapter 1, which is dFA over dV is equal to RA. Okay, so here we have a problem because the question doesn't ask us to write an equation with Fa, the molar flow rate, so we have to somehow replace the Fa with variables that we want in our final equation. So we know that Fa is the molar flow rate of species A in units of mole per time. Nu is the volume with units in terms of volume per time. And lastly, Ca is the concentration with units of mole per volume. So with that, we can see that Fa is actually equal to nu times Ca. Times nu times Ca. And again, and then we're also going to bring down our rate law, which is Ra equal to negative K times Ca. Now we're just going to rewrite this equation, replacing what we know. So instead of FA, we're going to put nu naught times CA. And then on our right-hand side, we're going to put negative K times CA. All right. Next, since we know that nu is a constant, we're just going to take that out of the derivative. So we get this right here. Okay, now let's go ahead and rearrange this equation. We're going to divide the CA over, multiply the dV over, and divide the nu naught over. From here, we just have to take integrals of both sides. And of course, we have to put bounds. Our bottom bound for the left side is going to be for the right side, C is equal to 0, which we again get from our diagram that we labeled previously. And then D is going to be V1. Okay, from here, we're going to go ahead and integrate this. And that gets us natural log of CA over CA naught is equal to negative K nu naught, which are both constants, times V1. Distributing the negative into the natural log, just to rearrange the answer a little bit in terms of V and getting rid of the negative, we get V1 equals nu naught over K times the natural log of CA naught over CA. And that is our final answer for part 2. All right, moving on to the last part of this question, part 3. We are given that nu naught is equal to 10 decimeters cubed per minute, and K is equal to 0.23 per minute. We're just going to use the equation that we derived in part 2 and plug them in. So V1 is equal to 10 over 0.23 times the natural log of CA naught over 0.1 CA naught. And from this, we can see the CA naught cancels out, so we're really just doing natural log of 1 over 0.1 times 10 over 0.23, which gets us a volume of 100 decimeters cubed.